Okay, we can start. Now, today we do planar graphs and discharging method. Maybe speak about far color theorem. Some things will be like more like history, introduction. So maybe no really, it's better to use little bit the slides, not to spend too much time on not necessary things to write down. When we do mathematics, we will switch off without slides, okay? So, day 3 officially a planar graph, discharging method, the four color theorem, and the generalizations. It is, they will get these slides, so it's history. I will speak about history. So, okay. I have to get time back. We spend too much time because we're too slow. Okay, this is day 3. Now, coloring planar graphs. Okay, you know already something, you know. In 1852, Francis Guthrie, somebody from England, was coloring the maps of England and observed that he can do it with 4 colors. And then he played a little bit, drawing arbitrarily map, and he always managed to do it with 4 colors. And then he observed that 4 colors are necessary, yes. Like here below, if we have a map like this, we need to use 4 colors. Okay? Here, which I use it on my talk, United States and India colored with 4 colors. Okay? So I speak a little bit about the history. We don't need, it's better to use the slides, yes. So he started believing that regions of any planar map, so you take a planar map, any can be colored with 4 colors such that any 2 regions that share a common border. It's not enough to share a vertex, common border of positive length. It can be very small, epsilon, but positive length. So you don't require here like this is country 1, country 2, country 3, country 4, country 5, country 6. You don't require country 1 and country 2 to have different colors because the border is only 1 point. It's not measurable. You want something measurable. Strictly, border should be border of Ci and Cj should be strictly positive border size, yeah. And here you have to color only, as it is drawn here, only these 2 differently, only these 2 differently, only these 2 differently, and so on. So actually you can color locally here just with 2 colors. Let's say brown. Another one is white, yes. Okay. So how it was the history? So it has rich history, this problem. Like, so Francis Guthrie told to his brother Frederic Guthrie about the problem, and Frederic in that time was attending lecture at the famous Professor De Morgan. You have heard the name, yes? De Morgan law in logic and so on. Okay. Then De Morgan wrote it later to Sir Hamilton, you know, Hamilton cycle. And this is also a famous English mathematician. And this is like the first official all this evidence where this problem is mentioned in this letter. Probably this letter exists somewhere, yes. And then nothing happened until 178, yes. When Arthur Kelly, on some meeting, there was London Mathematical Society meeting, I write it, meeting, yes, conference, workshop, whatever, he mentioned that that was happening in London, and then the things start becoming popular. Then Tide tried to prove it, giving a false proof. Kempe also tried to prove it, gave a false proof, yes. He would use the idea of Kempe and prove instead of 4 color with 5 color. Okay? And then this how started, everybody get involved. In that time, it was not people do just graph theory. In that time, mathematics was not so developed. Everybody was doing everything, and so it was like these all famous names, they were all trying to solve the 4 color theorem. Famous names from that time, but nobody was able to do it properly, yes. And this is how the Kempe chains were born. We use it in the edge coloring several times. In the edge coloring version, when we use Kempe chains, 2 colors, when you have H, Y, and J, we usually we have a path which may close, that is even cycle, yes, or stay like path. But when you use Kempe chain on vertices, it doesn't have to be path. It can branch, yes. It can be like this, Then you have like, yes. It can be any kind of graph, yes. But of course, if it has cycle, it has to be always even. It's a bipartite graph, actually. When you take 2 colors, it's a bipartite graph. And if we have coloring, we can swap A and J and get another coloring, yes. This is a trick which use it first Kempe, yes. Okay. This is more officially defined. I mean, I don't want to spend too much time on writing so much, but you know what is Kempe chain. So this is like formal, like the GB graph, phi is a proper coloring, C1 to 2 colors, and then AHP maximal must be in inclusion connected subgraph induced by these 2 colors. Take one component, let's say all of them, and change color C2 into color C1, color C from color C1 to color C2. You don't change the others, and that is like what you do. Yes, you just change one component in this Kempe chain. So this is here's illustration. We take blue plus red. We take this component, and this is all together here proper coloring. We take maximal one. We cannot take just part. We just cannot take just like 3. We must take all this part which is connected, We always take connected parts, otherwise it will be problem, yes. So you take this part, you see this is a connected thing. And we have these 2 colors, another here component, but they are apart, yes. So we can change here, we can change also here, on both, just one of them, and so on. We obtain new colorings this way. Okay? And here is how we swap it. When we swap it, we get this. So all these things you know well, so, okay? So now 5 color theorem, here with 5 color theorem, this is something that I want to prove, yes. So we may introduce here a new page. You see page. Okay, and I prefer it is like template of type, let's say this one with okay, with this color, and apply. So we prove now the Hewitt theorem. Actually, we're gonna prove it into two ways. One in Kempe chains, another with discharging, okay? I guess you like discharging here. So, theorem, 5-color theorem, yes. 5-color theorem. Okay, can you see this? Color theorem by Hewitt. And it says every planar graph is 5-colorable. Proof. We have G-spline graph. We can assume that the graph is critical. If not critical, we can remove some edges, some vertices, and we assume G is 6 critical. I don't know if we are needed. I don't know if we're gonna need this assumption, but it does give me some structure of the graph. Minimum degrees like that, maximum line, blah, 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 connectivity such, no separating triangle, and so on. Immediately give me some property of G. So when you color graph and you want to prove it 5 colors, you can always start with 6 critical graph. Okay? I don't need in my graph to hang vertex of degree 1 because I can remove it. If I color the rest, I put it back the color 1. That's always good start. If you want to color with 5 colors, your counterexample to be 6 critical. You starting by countercondition, you take the 6 critical graph, okay? And you don't know if you're really gonna need it, but you already have some structure. Okay? Now, this is a 6 critical graph. It's a planar graph. What we know in plane we always have, every planar graph has vertex of degree at most 5. So I don't have to spend time with 1 vertex, 2 vertex, 3 vertex, 4 vertex. My graph is 6 critical. I immediately go with 5 vertex. I just shorten the proof. Okay? So exist, just to use this, exist vertex V of degree 5. Since it is 6 critical graph, cannot be less, okay? By Euler formula, we know we have at most 5, but G is 6 critical, minimum degree for 6 critical is 5, so it's a 5 vertex, okay? Very short, no spending time, space. So I will draw this vertex. By minimality of the graph, by criticality of how you want it, you can say it, G, we assume, so this is V is 5 vertex, okay. We assume, we can denote the neighbors like x1, x2, x3, 4, x5. Okay? We assume, we can assume G minus V is 5 colored. Such coloring exists because the graph is critical, yes? Okay? And we can assume that we have here color 1, color 2. So we can assume in this coloring, the coloring is C, yes? C of X, I is I. We can assume like that. So X1 is colored by 1, X2 is colored by 2, X3 is colored by 3. Okay. So I need a little bit more space, so I will like move this copy paste, yes. And I need new page. It's move up. No, I want it here. New page. Yes. Okay. Maybe I move it a little bit. Okay. We need 5 colors. So we can assume this. Yes. If this is not a case, we could have a free color to put here, okay? Do we understand this? We have all 5 colors must appear around, because if some color is missing, I can put that color in V and it's done. So we can assume this is it. So, okay, now I apply Kempe chain, yes. Let's try, take a look, consider Kempe chain. We will denote like this: 2, 5, colors 2 and 5. What is important, 2 and 5 are not consecutive around when we go vertex V. 8V. 8 vertex X2. So we're gonna have something like here some vertices 5, then some vertices 2. So what we do? Can we change it? First, we can assume if X5 doesn't belong to this component, okay? Then we change everything. Maybe I can use some other color here. Then we change everything. Then we, instead of 5, put here 2. Instead of 2, we put here 5. Instead of these 2, we put 5, 5, 5, 5. But since X5 doesn't belong to this, this is case 1, yes? X5 stay 5, yes? And then we can put here color 2. And we then put, swap the colors in the chain and put 2 at V. Sorry? Oh, okay, we're gonna change it. Huh. So this should stay. So this is, we should change this into something more visible. We have that. What about this one? This is better? Yeah. But not many colors here, so. So, okay. So we can assume that the 2,5 Kempe chain, which contain X2, contain also X5, yes? So we have situation like this. We have situation like this. With this is vertex V here. This is X1, X2, X3, X4, and X5, and then we have this Kempe chain. This is color 2, 5, 2. You see this well? Okay, 5, 2, 5, 2, 5. And maybe also here some 5. And maybe here also some 2, and so on. But look this path. Look this path. Look this path. Oh, I'm hammering this. Why is this? Look this path. Together with V. It's a cycle. Do you agree? And now, inside the cycle, which vertex is inside? Yeah, X1. I need here color 1. And now, this outside the cycle is, let's say, X3, yes, also X4, but X3, yes. So, and now we will take a Kempe chain 1, 3. And this Kempe chain cannot connect X1 and X3. If it connects, it will have to go through this path, but this path has only colors 2 and 5, and you will need to have on this path vertex which is color 1 or 3. So I will write it now slowly. We can put some other colors here. Yeah, and we can put some, okay, or maybe here we put color, instead of this we put blue. Okay, so purple path, or with the pinky path, or whatever, pinky path. Pinky path. With X2 path, yes. Between X2 and X5, and V together form cycle say C. X1 belongs inside the cycle and X3 belongs outside the cycle. No, it's not cycle C1 but just C. So now consider Kempe chain at X1, let's say, at X1. So now at X1, the Kempe chain let's make it. We're gonna have this 3, 3, and then maybe 1, 1, 1, 1. But all these Kempe chain component at X3, X1 will be inside the cycle. Is inside the cycle. Cycle is this. Cycle is this, yes. So when we change the colors, so we put here now 3, we put here 1, 1, 1, 3, 3, 3, 3, and so on. We don't go outside, we stay here. This vertex will still stay color 3, and this vertex will still have now color 3. So now color 1 doesn't appear around, yes? So we put 1 here. Okay? Kempe chain at X1, swap the colors, 1 and 3 there. Know that X3 stay colored by 3. Since the Kempe chain is inside the cycle, is inside the cycle C, and then put 1 at V, and then finally color V by 1. That's it. That's the Hewitt proof. Okay? This is written here. You're gonna get the slides, yes. Maybe not in the best way, but, and this is this illustration, what we had, yes. We take 2, 5, and then we change now. 1, 4. Okay, on this drawing is 1, 4. We took 1, 3. It doesn't matter. And so on, okay? We have still such things, we don't have to write, no need to write it. So nowadays, 4-color theorem is solved. It was solved by by Apple and Hacken. But how they saw it, Hersh introduced the discharging method. And then people start doing discharging, finding reducible configuration, unavoidable set of configuration, and so on. And then, Apple and Hacken, we are at the University of Illinois. In that time, the supercomputers were appearing. Yes, those supercomputers are weaker than this one, but for that time it was advanced, and they, with use of the four-color, the computer, they managed to prove the four-color theorem. They prove this very huge. If we count in the number of configuration, it was like 3,000 configurations. Okay? Nobody ever checked that, if this is really correct. Nobody checked it. But in 1995, Neil Robertson, Sanders, Paul Seymour, do you know the name Paul Seymour? And Robin Thomas gave new proof, which was like little over, I think, around 600 configurations. Around, yes. So it's like 5 times shorter proof regarding the number of configuration. Each of these configurations you have to prove it's C or D reducible. We will explain what is next. And show that all this set of 600 configuration is unavoidable. Unavoidable means every planar graph contains one of them, yes. Okay? So then several people independently, including some my colleague in Ljubljana, check their proof. So this proof is checked by several people independently, and everyone reported is correct. And Apple Hacken proof was 3,000 configurations. It was a little bit too much to check it. And in that time, the computers were not so good and not so common. Usually, university had one huge building like this one. It was only computer. It was like that. Now we have these small machines which are much better than that computer. Now it's different. Now it's much easier to check it. Now even if you want, you can check it yourself. You need a little bit programming, and then running, testing reducibility and so on, then applying some rules and so on. And it's possible to check it by yourself. It's not like you can do it in one day too. You will need a little bit more, yes? Maybe the computer will run one day or two, but you have to program it and so on. You have to be able to do that, but it's doable. So people check their proof and report it is okay. But this proof is still based on computer calculations. We don't know pure mathematical proof. That's job for you, yeah? To find new proof, yeah? Okay? Now, here the 700 reusable configuration. Okay, 700, yeah. The other one was over 3,000, okay. 32 rules. I will give example of these configurations, yes. Independently out of that, people were trying many different things to prove. Now they discovered the discharging method and so on. Then, okay, what about triangle-free graphs? Like one can say, what about triangle-free graphs? Do we really need 4 colors? Or we can do it with less colors? What about triangle-free graphs? Does anybody knows? triangle-free graphs, planar graphs. Grosch proved that it can be done with 3 colors. It's an Austrian guy. It can be colored with 3 colors. And the proof is not very difficult, 2-3 pages maybe, yes, let's say. I think the best proof is maybe by Katz and Thomason with using extension about least color inversion and about Kempe chain by Zdenek Dvorak. Yes. This guy, Zdenek Dvorak, was doing this compiler optimization. Yeah, this is the guy. Yeah. So there are 2 proofs. Yeah. For least version, GERT5, and then it can be reduced to usual color to GERT4. See Katz and Thomason proof. Katz and Thomason. For Kempe chain, proof, look, Zdenek Dvorak. Okay. You can, I know that you can find this proof online, yes. In 3 colors, yeah. This is like proofs of Grosch theorem. Yeah. Yeah, but we speak about triangle free. And actually, Thomason proved it with GERT5. GERT5, yes. For least colorings, yes. Yeah, but they reduce somehow. They do something. If you want to use all 3 colors the same, I think the Katz and Thomason maybe imply in some way the Grosch theorem, yes. Because I think if you have Grosch theorem, I think if you have 4 cycle, you can reduce it somehow. And then you stay at 5 cycles and more for usual coloring. And then you apply Katz and Thomason, least version. But that's not necessary to complicate. I think Zdenek Dvorak has very nice proof with Kempe chains for Grosch theorem, yes. I didn't state Grosch theorem. So this is Grosch theorem. Every planar graph without triangles, so triangle free, is 3 colorable. People try many other things, like this. Now, opposite to this, this graph has no face which is triangle. But let's take a graph which all faces are triangles, but extra assumption every vertex is of even degree. You know, every vertex is of even degree and it's a triangulation. So it looks like this locally. It's degree 4. Okay, let's say this is degree 6. So this is degree 6. This is maybe degree 8. So we have all faces of size 3, it's a triangulation, but all vertices are of even degree. And you know, if you now try to color it, okay? Okay, oops, better not touch it. I use some other color. You know, I will put here color 1. Okay? Then I put 2. I go around this vertex. 3. What I can put here? 2. Here. 3. I can go now here. 1. 1, 2, 1, 2, 1, 2, 1, 2. I can do it, yes? One, two, 1, 2, 1, 2. And here, look. Here is vertex 2. 1, 3, 1, 3, 1, 3. Yeah? And so on. Actually, you will color the graphs. You will always color the graph like this. If all vertices of even degree and every face is a triangle. And this is very old result. We are not going to prove this. We don't have time. But it's very beautiful theorem of Heawood, the old Heawood, which proves 6 coloring of the plane. So a planar triangulation with every vertex of even degree is 3 colorable. It's a kind of opposite of Gauche. Gauche requires no face of size 3 and says nothing about the degrees of the vertices. Here we allow the Woresting to have a 3 face, but we require every vertex to be just of even degree. And then it's always colorable. This could be a very nice exercise. This is doable. Maybe you can solve it. Okay. Should we make small break? 5 minutes, yeah? Okay? He doesn't have 3 vertex maybe. Okay? Such things, yes? Just to get rid a little bit of not necessary things. Like good start is some critical graph if we speak about usual coloring, okay? Get rid of, so I just like, this is philosophical part, yes. Get rid of, how I can say, how I get rid, like this, of easy things. Okay. Then come harder things. That we say reducible things. So get rid of easy things is like, okay, G has no 1 vertex. Or maybe also 2 vertex. Like, let's say we like to color it with 4 colors. We don't need 1 vertex, 2 vertex. If G is a minimal count, for example, doesn't have 1 vertex, doesn't have 2 vertex, doesn't have. These things are also reducible. But how easily reducible immediately. Then you study some configurations, depending of your coloring. Okay, maybe we don't have 2 triangles adjacent. We don't, examples. We don't know 2 triangles adjacent. And we have to prove this. We do like prove maybe 10 lines, 15 lines, and so on, to prove that for our coloring, our counterexample doesn't have such configuration. Or maybe, other examples, we don't have 2, 3 vertices adjacent. Or maybe even 3, 4 adjacent. We don't have, let's say, we don't have, not have, let's say, I will write it like 3 minus 4 minus vertices. Vertice. Three minus mean 3, 2, 1, yes. 4 minus mean 4, 3, 2, 1. More compact way, yes. Or maybe like this configuration. Maybe I cannot get rid of 3 triangles, but here is a 5 vertex, a small vertex, let's say. Everything is at least 5. Or maybe 5, 5, 5, depends on our coloring. So many such reducible configurations. You reduce them. You say, my counterexample doesn't have it. Okay. Now you have some structure in your graph. Minimum degree 3, not 2, 3 cycles together, not 5 vertices on a triangle and such things. This will give you later some, when you're gonna redistribute the charge, will make you something to conclude and come to counterexample, okay? Initial charge. Here we use the 4-color theorem, yes? We assume graph is connected. 4 colors theorem says, Euler formula. V minus E plus F is 2. And you can rewrite this, very often, most common, in this way. If we go through all vertices, this is V of, let's say, D minus degree of width minus 6. Fuse go through all faces. Okay, twice the length of the face. You can also say degree of the face. Minus 6. Okay. Is how much? Anybody knows? Well, minus 12. Oh, exists also something like this. 6 minus degree of vertices. Six minus 12 F. And here, what are you going to put? What? This? Why will be 12? Why is minus 12? Why is 12? I will say you're wrong. Sorry? First is minus 12. Okay, let's do the first minus 12. And the second plus 12. Okay. So you can easily check if you're not sure. Take K4, and if you put here everywhere 3, here will be everywhere 0, 3 minus 3, 4 vertices, it must be minus 12, yes. and this is 12. Okay, you can have any kind of you can have many variation of this. Yes, you can take it like maybe you have seen also in this form. -4 plus length of the face is -4 -8. Do you have the most general version? Do you know the most general version? The most general version is, do we have space here? Is it seen easily? Okay, we can, okay. We can clean this, yes? Or like this. Maybe just this. And the more general version, which I know. Let's alpha plus beta is 3. So if you take alpha is 1 and beta is 2, you get this one. If you take vice versa, beta is 2 and alpha is 1, you will get here 2 and here you will get 1. Do you see how we get this one from this? Take alpha equal beta equal 3/2. Then you will cancel this -12 into -8. Yeah, you can check it later. Yeah. Then let's go on. We have initial charge. Then we invent some rules. Depend what is our initial charge. Let's say we stick to this one. Let's say we stick initial charge. Let's say is d of v -6 plus 2L of f -6 -12. You see, if we take an initial charge like this, what vertices and faces will have negative charge? Here will be only 3 vertices under the charge. 3 charge will have initial charge -3. 4 vertices will have -1. And 5 vertices, no, -2. And 5 vertices will have -1. Okay. Now we have to apply some rules that make these vertices positive charge to have it. Like maybe examples. Yeah?
Charges here.
Charge?
Yeah,
When we have initial charge, yes, we took you don't know that. Okay, I thought you know this. So we give to every vertex initial charge this one. Initial charge. Charge of a vertex V will be dV minus 6. And to every face, we give charge, initial charge, L twice LF minus 6. Sorry, I didn't say that. I thought it's, you know that, okay. Now, I can ask, what is the total charge? If I go through all vertices, sum the charge, and then go through all the faces are the charge, then the total charge will be, which is negative. Or 12 if you take other way around, yeah, so depends what is initial charge. So we start with this, let's say, this is initial charge for vertex, this is initial charge for face, and total charge is minus 12. Now we will apply rules. I give you charge, you give that charge, so we give each other some charge. But what will carefully, under some rules we do this. The idea is, at the end, everybody has at least 0 charge. If everybody has at least 0 charge, total charge will be at least 0, very likely positive. But we didn't put something into the pocket. We didn't still charge. We just, what we have sent here and sent there, and that will be contradiction because minus 12. So we will sending charge, carefully construct our rules under condition that these reducible configurations are not into the graph. So we will assume that this doesn't exist, this doesn't, so we can then send little more charge, or some vertex can receive little more charge because we know this doesn't exist. And I can send little more charge and I will not go under 0 because I know this doesn't exist. So under this assumption, we will create rules which will send. Usually the rules are like this, like let's say examples of rules. Let's say, let's say 4 vertex, and this is a 3 vertex. Okay. Now look, 4 vertex, this is I have 2 values. And this is a 3 vertex. Maybe I have 3 of them, yes? Then I have to send 1/2. I don't want to go negative, yes? If here is a 3 vertex, here is 3 vertex, here is 3 vertex, I can afford only to send 1/2 to each one. And that will a little bit help. But, this is very important. If 3 is reducible, if I prove it before that 3 is reducible, how many 3 vertices I can have around? How many? Then I cannot have 3 or 3. I can have 3. Oops, sorry. I cannot have 3 or 3. I can have, oops, sorry. I can have 1 3 here and 1 3 here. Yes. Here is maybe 4 vertex and here is maybe 5 vertex. Or let's say like this. Let's say it's 4. So if I have proven before, 3 is reducible, I will represent 1/2, 1/2, 1/2. What I will do? I have here 2 charge, initial charge, yes? 4 phase have. What I will do here? What is smart to do? So if we have situation like this vertex, this phase has initial charge 2 multiply 4, 2 multiply 4 minus 6, it's 2. This has charge 2. Let's simplify it, yes. Maybe let's say here 6. Then I can send here 1 and here 1. Instead of sending 1/2, I can send 1/2. This is how we do, yes.
Donate 3 and take some of number.
Integrate
3 and take a charge from another.
Yeah, you can have like that, but then instead of taking 3 and then taking 1, you can maybe directly send from the other one. You can do that, yes. But sometimes you do that way, just to be easier to explain maybe, and sometimes you send and also receive, yes, or sometimes you don't do that, you directly send, yes. This is a question of taste. What do you prefer? Yeah, sometimes like that, yeah, or what is easier to state. Now, under assumption that we have some reducible configuration, we will redistribute the charge like that. So this is it, yes, the discharging method, yeah. Assuming that G doesn't contain some reducible configuration, we send charge and we assume that we obtain later, because some configuration doesn't exist, are reducible, that at the end every vertex and every phase will have positive charge, which means the total charge will be all positive, which is contradiction that with the initial charge is negative. And this is how this contradiction will prove our theorem. Okay? So here's one example.